Hello everyone, today I would like to talk about the photoelectric effect. You know the light, we also call it the photon. This is the, you can say, the tiny packet of energy. The photon, it is, we can consider like a particles, okay. It is, you can say, light particles, and it is the tiny packet of energy, and it has an energy E. This is equal to H times F. This is E is the energy. F, you know, F is the frequency. Energy, you can use either joule or you can use electron volt also. Electron volt, okay. The unit of energy is joule, or in modern physics, people they use electron volt. And if you would like to know 1 electron volt is EV. This is electron volt. 1 EV is equal to 1.6 times 10 to the power negative 19 joule. Okay, 10 to the power 19 joule. If you want to convert electron volt into joule, you have to multiply by 1.6 times 10 to the power negative 19 joule. Okay, so here is the energy, F is the frequency. You know the unit of frequency is hertz. Okay, simply you can write down Hz. This is the unit of frequency. And what is H here? H, this is the constant, and this is 6.626 times 10 to the power negative 34 joule second, and this is called as the Planck's constant. So it is better to know this number. The Planck's constant H equal to 6.626 times 10 to the power negative 34 joule second. So this is a Planck's constant. And this formula to calculate the energy of photon, or the photon, it is tiny packet of energy. It is the light particles. Okay. And this is from the quantum hypothesis. Actually the Planck's quantum hypothesis. Now the energy of any vibration, you cannot have any value of energy. Like the energy of any vibration, the molecular vibration, you have to write down the energy is, you can write down like this, 1 HF, 1 times HF, or that is same as HF, or you can write down 2 HF, okay, 3 HF, or 4 HF, but you cannot write down 3.2 HF. You cannot do this. So it is kind of discrete number, 1, 2, 3, 4, 5, 6, 7, 8, like this. Okay. So 3.2, no, this is not possible. So we can say that energy is quantized then. Energy is quantized. Okay. Okay, by saying this, now let us focus the photoelectric effect. So what is photoelectric effect? I told you photon is the light. Simply the photon is the light. Now what happened is, let us suppose you have a metal. This is like a metal, like a sodium. And the metal has an electron, of course. And if you strike the light here, shine the light there. Here you have a metal, and you strike the light here, photon. A light is the photon. So this is a light. We also call the radiation. Okay, and there is an electron. What happens is, if you throw the light onto this metal, then what happens is this light knock out the electron from the metal surface. This electron, the light knock out the electron. So this is the electron. Knock out, eject the electron from the metal surface. when you throw the light onto the metal surface, the electrons are ejected from the metal surface. This is what we call the photoelectric effect. This electron, the ejected electron, we call the photoelectron. Photoelectron. But there is of course some condition. Any light cannot eject the electron. Any light cannot knock out the electrons from the metal surface. There is some condition. I mean, the incident light, this light, it must have some minimum energy, so that this light can knock out the electron from the metal surface. So the ejection of electron from the metal surface by striking the light of suitable frequency, that is called as the photoelectric effect. So this is your incident light. It has an energy E is equal to HF. Okay, so F is the frequency. I already mentioned this. So you can write down the ejection or emission of an electron from the metal surface by striking the light of suitable frequency, or you can say energy also. Light of suitable frequency is called photoelectric effect. So this is called, so simply knock out the electron from the metal surface by shining the light. Okay, so that is a photoelectric effect. Okay, so if you want to see the experimental setup, you have something like this. You have a chamber here. This is a chamber. Okay, and right there you have a metal plate. This is a metal plate. This is the metal plate, and there is right here, this is, you can call collector here. And what happened is, this collector, it is connected to the battery here, and this is, you can connect the, this is the emitter and connect this. So this is your emitter. Emitter measures the current. So this is a battery, this is positive, this is negative. Okay, this is a collector, this is, let me call C, this is a plate P, and this is like a metal plate. And here you have a light source. Light strikes here, light strikes there, incident light. And what happens is, electrons eject from here. And look at this. This is collected. This is connected to the positive terminal of the battery. So if the electrons are ejected from here, these electrons, this is ejected electrons, we call the photoelectron. This electron is attracted toward the collector. This is positive terminal because photoelectron or electron has a negative charge. So this negative charge electron is attracted by this positive terminal. Then from here also you can write down like this. So another electron here. So the incident light knock out the electron from here, from there, and this ejected electron, the emitted electron, we call them photoelectron. They have the same property as our regular electron. Okay, and this is negatively charged, this is negatively charged. So this negatively charged electron attracted by this collector and it goes there, right? And look, if one electron is ejected from here, so there is a gap then. To fulfill the gap, the electron from here goes there. That means there is a flow of electron here. That, you know that the flow of electron is called as the electricity. So you can see the current here then. photoelectrons attracted toward the collector and it goes to the positive terminal. Now there is a gap, then electron from the battery, it goes to the plate here to fulfill the gap here, the deficiency of electron to fulfill that. So electron from here goes there. So there is a flow of electron, then you can measure the current here. So this is how it works. Okay. So this is the experimental setup. This is your incident photon or incident light, whatever you call incident photon, or you can say incident radiation or incident energy, whatever you call. This incident photon has an energy E, and this energy in the energy of the incident photon E, this is H times F. H is the Planck's constant and F is the frequency. Now when this energy, I mean this light incident here, it knock out the electron. So what happened to this energy then? What happened to this energy is certain amount of energy is utilized to knock out the electron from the metal surface. If the incident photon has energy more than the energy required to eject the electron, what happened to the rest amount of energy then? Let us suppose to knock out the electron from the metal surface, you need, let's say, 2.3 electron volt energy. For example, let us suppose to knock out the electron from the metal surface, let us suppose you need 2.3 electron volt energy. Here you have a metal and this is the electron. To knock out this electron, let us suppose you need 2.3 electron volt energy. But if the incident photon has energy like 5 electron volt, for example, I randomly chose the number, okay, this is not my experimental data. Let us suppose the incident photon, incident radiation has energy 5 electron volt. But just to knock out the electron from the metal surface, let us suppose you need only 2.3 electron volt energy. Okay, only 2.3 electron volt energy. So what happened? This 5 electron volt energy, 2.3 electron volt is utilized just to detach, to knock out the electron from the metal surface. So how much left? 5 minus 2.3. How much? 2.7 something? 2.7 electron volt. So what happened to this energy? This energy is absorbed by the photoelectron and it moves. So the photoelectron move. If the particle move, it has a kinetic energy. So energy associated with motion, that is a kinetic energy, 1/2 mv square. We talk about that in chapter, I think 6 or 7 in mechanics. Okay, so if the incident photon has an energy, let us suppose the incident photon has an energy E, this energy is split into like the kinetic energy of the photoelectron, you can write down Ke max, maximum kinetic energy, plus you can write down omega 0. Now what is E? Is the E energy of incident radiation, or you can write down photon. So this is E equal to, you can write down HF. Okay, Ke max, this is simply, you can write down 1/2 mv max square. This is maximum kinetic energy of the photoelectron, maximum kinetic energy of photoelectron. You know the kinetic energy formula is 1/2 mv square. So it is if the kinetic energy is maximum, then speed is also maximum. So I write down 1/2 mv max square. What is m? What is m here? M is mass of electron. This is mass of electron, and this number m is 9.1 times 9.11 times 10 to the power negative 31 kg. Okay, so Ke max is 1/2 mv max square, and is the mass of the electron, 9.11 times 10 to the power negative 31 kg. You need to know this or write down in your formula sheet. Okay, and what is omega 0 then? What is omega 0? Omega 0 You can write down HF0 also, and this is we call work function. Work function of the metal. So what is work function then? What is work function? What is f of 0? F of 0 we call threshold frequency. Threshold frequency. So you have a two new term here. Omega 0, which is work function, and f of 0, this is your threshold frequency. So what are these? Okay, we'll talk about it, but let me modify this equation. So E is the incident photon, energy of the incident photon. You can write down HF equal to, you can write down Ke max, but please note Ke max is 1/2 and V max is square, plus if you need, you can write down HF0 also, because omega 0 is H times F0. You know that H is the Planck's constant, 6.626 times 10 to the power negative 34 joule second. Okay, so this is the photoelectric effect equation. Okay, whatever these two, it's the same equation. Okay, not two different equations. The only thing is I write down the E as H times F and kinetic energy, and omega 0 is the work function, but work function is also the energy. That is why H times F of 0. Okay, so let us define what is work function and what is threshold frequency then. Work function, omega 0. I told you that, like if you simply strike the light on the metal surface, you cannot emit the electron from the metal surface, because the incident light has a certain minimum energy. Okay, so the minimum energy required to eject the electron from the metal surface, that is called as the work function. Okay, so the work function is the minimum energy required to eject the electron from the metal surface is called work function. And the work function is simply, it looks like a W, actually it is omega. You can write down omega 0. This is equal to H times F of 0. And this is also the energy. So the unit is, you can write down joule or you can write down electron volt. It is a work function, it is the energy. So the minimum energy you need to eject the electron from the metal surface, that is called as the work function. And of course, different metal, they have a different work function. Different, it is like a characteristics property. So different metal, they have a different work function. Okay, so the work function is simply the energy, minimum energy you need to knock out the electron from the metal surface. That is the work function, and the unit is joule, or you can use electron volt also. And here F of 0, we call that threshold frequency. The threshold frequency you can define in the similar way. Threshold frequency, F of 0. Okay, so this is the minimum frequency, because you know that the energy depends on frequency, because the energy formula E, this is equal to H times F, right? So if the frequency change, energy change. Okay, so you can define the minimum frequency required to eject the electron from the metal surface. Metal surface is called threshold frequency f of 0. Okay, so if you like to plot the graph between the kinetic energy and the frequency of the incident light, so what happened, the shortened energy you need just to knock out the electron from the metal surface. Okay, so it is like this. If you plot the frequency here and plot the kinetic energy there, you can plot maximum kinetic energy also, in different cases, you need a certain, you cannot start from here because you need certain minimum frequency to knock out the electron, so maybe somewhere there like this. So this is right here, you can eject the electrons. Now if you increase the frequency of the incident light, what happened to the maximum kinetic energy? Then it also increases linearly like this. So you need a certain minimum the frequency to knock out the electron, f of 0. This is what we call the threshold frequency. Okay, and if you increase the frequency, then your kinetic energy also increase linearly. Therefore you need the certain minimum frequency to knock out the electron from the metal surface. That is what we call the threshold frequency. If the frequency of the incident light is less than the threshold frequency, you cannot knock out the electron from the metal surface. Okay, so this is about the photoelectric effect. So from this photoelectric effect, you can conclude that the light behaves like a particle also. Then simply when the photon strike here, what happened to the photon? Simply photon disappear there. All energy transferred to the photoelectron, or the certain amount of energy is utilized to knock out the electron from there. Okay, so here I want to talk about the photon little bit more. The photoelectric effect is done, so the only thing you have to know is the definition of photoelectric effect, and what is threshold frequency, what is work function, and what is photoelectric equation. Okay, this equation, your E equal to Ke max plus omega 0. This is your photoelectric equation. You can get the numerical problem from here also, very simple numerical problem. And we talk about the photon, the tiny packet of energy, small particles. That is, we can simply consider the packet of energy. Okay, is h times f energy. But light, light is the wave, because light can show the property like interference, diffraction, polarization. So light is the wave, electromagnetic wave. And from the photoelectric effect, we came to know that light is of particles. So light has a dual property then: particle nature, wave nature. Light has a two nature, like a particle nature, like a photoelectric effect. Prove that. And there is another effect also, we call the Compton effect. We do not talk about this here. Simply Compton effect is when the light strike on the metal surface, then simply the photon is scattered. Okay, that is what we call the Compton effect, but you don't need that here. So the Compton effect also shows the particle nature. We have a photoelectric effect, Compton effect, like that. So that is the particle nature. And we have a wave nature. The light shows the wave nature, like interference of light, polarization of light, diffraction of light, something like that. So light shows the dual property, duality. Now, a person, you can call scientist, Louis de Broglie, proposed that if the light is particles and if the light is wave, like then like if your car is moving, object, particle, object, then the moving object, we can also say that the moving object also behave like a wave. Then matter wave, matter wave. Like if the electron is moving, electron is the particle, object. So if the electron is moving, we can say that it behaves like a wave then. So if the particle, if the object is moving, matter is moving, matter. If the matter is moving, then the wave there is, we call the matter wave. If the object is moving, we can say that it behaves like a wave, and that is what we call the material wave, matter wave, particle wave, whatever you call. So if it is a wave, then you need to know the wavelength. And the wavelength of matter wave, wavelength of matter wave, it is a lambda. This is equal to h over p. What is lambda? Wavelength. What is h? Planck's constant. H, I already told you, this is 6.626 times 10 to the power negative 34 joule second. Planck's constant. Lambda, wavelength of matter wave. Actually, we use the same lambda to represent the wavelength. What is p? P is mass times velocity, momentum. This is a linear momentum. Linear momentum. Okay. So this formula you can also write down lambda. This is equal to h divided by mass times velocity. So if the object is moving, like the electron is moving, in that case, what is the mass? This mass is mass of electron. So whatever, if this particle is moving, if it is moving, we can consider this is like a wave. So if it is like a wave, what is the wavelength of matter wave then? You have to use this formula. You need to know the mass. So like if you have small particles like an electron, proton, whatever, then you need to know the mass. It is either given or you have to calculate that. So this is the wavelength of the matter wave. And this is also called as the de Broglie hypothesis. Okay, so this is better to know. So this is all about the photoelectric effect and the de Broglie hypothesis, the matter wave length. Okay, so better to know this. Okay, thank you.